Okay, so let's take a look at the last part of section 6.1. And there's two things in it. One of them is arc length. So we're going to look at a formula to find the length of an arc. And the other thing that's in it is what's called angular velocity, which basically means the speed of something spinning that moves in a circle. You can measure it in like RPMs or something like that. All right, so first of all, I'm going to draw a sketch in a second. But in this sketch, I want to tell you something that's true. Arc size and angle size are directly proportional. Okay, what does that mean? Arc size and angle size are directly proportional. That means if you have a circle, and inside that circle you draw an angle. Okay, I have two angles. I'll talk about why I have two in a second. But if you draw an angle and you make the angle twice as big, you make the arc twice as big. If you make the angle half as big, you would make the arc in red half as big. So there's a connection between theta 1 and S1. I'm not saying they're the same. I'm just saying if you double the size of one, you double the size of the other. Any question on that idea? Directly proportional? Okay. And when things are proportional, we can set up in math a proportion. Okay. So that's where we're going to be going with this diagram. But to set up a proportion, you need four things. A top and bottom on the left, a top and bottom on the right. If you look at my diagram, I have four things. I have inside the angle that's on the right, that's theta 1. The rays of that angle come out, hit the edge of the circle right there. I connected the arc between those two circles. I'm going to call that arc S1. Then on the other side, I drew another angle, which I'm calling theta. The sides of that angle come out, hit the circle right here, and I connected the arc between those 2 points. I'm calling that arc S. And this arrow means nothing. Okay. Any question on the diagram? All right. So now, to figure out a formula for the length of an arc, okay, I want to come up with a formula. So you tell me something, and I tell you back the length of the arc. You've got to have what I call a starting point. You've got to have something you already know. And it's kind of a simpler example I just want to show you. Let's say you wanted to convert feet to inches. What's the conversion between feet and inches?
1 foot equals 12 inches.
1 foot is 12 inches. So now that I have that starting fact, you could tell me any number of feet or inches, and I could convert it. Say you said, how many inches in 6.5 feet? I just fill in 6.5 feet, how many inches, and then cross multiply to solve. But the key is you have to start with something you already know. Okay, how do you know this? Well, you were told it. You were told that that's the conversion between feet and inches. Well, we're going to do the same thing with the circle diagram. We're going to have to start with a fact I already told you yesterday. And using that fact, we can figure out anything we want. Okay? So just because this number is a 1 and this number is a 12, does that mean I can only put a 6.5 right there? No, I could put any number I want. I could do 7 feet, 12.2 feet, any number that I want. So just because that side is something specific, it doesn't limit what you can do on the other side. Okay. So now let's try to figure out what we can do here. Okay, I'm looking for that starting fact. Okay, in 1 foot, there's 12 inches. All right, so let's look at this angle, theta 1. If you let theta 1 be a certain size, you will automatically know S1. It's automatic because of something I said yesterday. Does anybody remember what I said about theta 1? If it's a certain size, then that arc is automatically the same as something else.
Yeah. The angle would be 1 radian if the arc is equal in length to the radius.
Yeah. If you say, just as a starting point, just like Evan picked 1 foot 12 inches, okay, you just pick that as a starting point. If we pick, let theta 1 be 1. Let it be 1 radian. That's going to be our starting point. Then, because of a fact I told you yesterday, the definition of a radian says, if that's 1, the size of the arc and the size of the radius are exactly the same. So if you decide to let theta 1 equal 1, then the arc is exactly the same as our radius. That fact right here, this is going to be like our 1 foot 12 inches. It's a fact that's true, and we can use it to figure out anything else we want. Okay, so let's set up a proportion just like we did here. Okay. And there's lots of ways you can set up a proportion as long as you're consistent. Set it up the same way on each side. Let's compare the first angle to the first arc. And then I'm going to compare the other angle to the other arc. So I put angles on top, I put arcs on the bottom. Again, there's many, many other ways to set it up. Just be consistent on each side. And now I'm going to fill in our 1 foot 12 inches. I'm not really putting a 1 and a 12. I'm just, in general, I'm going to fill in the starting point, which is 1 radian gives me a radius of r. So 1 radian gives me a radius of r. That's my starting point. Now, the other side, I'm just going to leave blank. Okay? That's where you would fill in, well, is it the number they give you? Okay, whatever they want you to convert. So leave that as theta over s. Now, usually this formula is written with the s by itself. Does anybody remember the name of the technique you use to solve a proportion? It's 2 words. Cross multiply. So let's do that times that. What's s times 1? S, and then r times your angle. There's nothing else you can do with that. It's s equals r theta. Okay, and that's the arc length formula. Okay, so to find the length of an arc, you take the radius and multiply by the angle. But way back at the beginning, when we started this problem, we assumed something about the angle. We said, suppose that the angle was 1, what was the unit? Radian. So way back at the beginning, we assumed we were working in radians. So that means if you use this formula, you have to use your angle in radians. If you plug degrees into that formula, it will come out wrong. Okay. Right, and when we're using that formula, there's really 3 things they could ask you for. They'll always give you 2. So they might give you r and theta and say find s. They might give you s and r and say find theta, or the other combination. Okay, but you'll always know 2 out of 3. Okay, everybody have the arc length formula. Okay, when they give you an arc length problem, they can either write it all out, okay, describe it, or they could just give you a picture instead. Okay, I did both. But on most problems, you're going to get one or the other. Okay, so here's a picture of what it's saying. They want the length of the arc. Okay, that's in red. Okay, that arc is part of a circle. And the radius of the circle is 2 inches. And the angle in the circle is pi over 4. Okay, so find the length of the arc in red. It doesn't say if we should round it off, okay, or leave the answer with pi in it. So I'll do both. I'll show you how to do both. All right, so Braden, what's my formula for the length of an arc? We just came up with that.
It's the radius and times the angle, right? And
Yep.
radians.
And that's going to equal your
Arc length.
Arc.
S.
So S equals r theta. Julia, what's my radius in this problem?
2 inches.
Yeah, radius 2. So we're going to fill in 2. And Andrew, what about my angle?
Pi over 4.
What's the units on that? Like, we talked about 2 ways we can measure angles. Which one is that using?
Oh, that's using radian.
Radians. Is that what the formula is supposed to be?
Yeah.
Yeah, the formula is supposed to be in radians. They gave me an angle in radians. I'm good to go. So r times theta, or if you don't want to put it all over 4, I mean, you can do it like that too. It's the same thing. So just multiply straight across. You're just going to get the 4, which is what I just had originally. 2 times pi. And that's going to reduce to pi over 4. But now we want to put the right label on it. Okay? We just solved for S. What's S again? Thank you. What is S? S is the length. Okay, so I go back to my problem and I look at the units they used for length. So if you put a piece of string on that red arc, it would be pi over 2 inches. That's the answer. Okay. How much is that? Well, it's roughly, if we, I know I said just use the pi button, but that's more than accurate for what we need. So it's about 1.57 inches. Okay, so in that formula, S is a length. So it should always have inches, feet, centimeters. R is also a length. Theta is an angle. Any questions on that? Okay. Let's try this one. Okay, so no picture this time. So here it says find the radius. So now you're solving for a different variable. Find the radius. If the arc length is 3 pi and the angle inside the circle is 60 degrees. Okay, so it's the same formula we just used. Can I just take all the numbers that are in that problem, plug them right into the formula right now? No, one of them I need to fix it. What number here do we have to fix? 60. What do we have to do with it? Change it to radians. How many times does 60 go into itself? Once. How many times does 60 go into 180? 3. So your angle is pi over 3. Now you can plug it. 3 pi. Where is that going to go? What letter? That's S. And then your angle, that is going to go right there. So you get 3 pi equals R times pi over 3. Now, you're multiplying a variable by a fraction. Does anybody remember what you do when you multiply by a fraction? You flip it, right? Like if you had 2/3 x equals 12. To get x by itself, bless you, you flip it. You multiply each side by the reciprocal. And then you do it out. Okay, same thing here. What's the reciprocal of pi over 3?
3 over pi.
3 over pi. 3 over pi. 3 over pi. Pi's are gone. 3's are gone. Pi's are gone. So I'm left with my radius equals how much? 9. And radius is a length. Measures how long something is. So what should it be in this problem? Feet. Okay. Any questions on that one? Okay. In the last type of problem they could give you, they would tell you the S and the R, and you would find theta. You would just divide S by R, and you would get theta. Okay. Any questions on how you would do the third type? I didn't have one made up for that. But if you could do the first two types, the third type isn't really any harder. Okay, so that's arc length. So that's the first thing. Okay, second thing we're going to look at is angular velocity. Now, you can measure angular velocity in different units. Okay? It measures the speed of something spinning. The default unit the book uses is radians. I think it's more common in real life to see a lot of people use revolutions. And it's easy to convert between the two. If you know how many radians in one revolution, you can convert. Okay. But before we look at a problem, I just want to look at why does this even exist? Why does the concept of angular velocity, why is it used? Like you see it, you do see it. Certain power tools might spin at a certain RPM. Your engine, if it has a tachometer, it measures the RPMs. But why? What's wrong with just measuring speed the way we always do, like miles per hour? Why is there this revolutions per minute thing?
Because we have wheels.
All right, yeah, it has to do with things spinning. Okay, we're going to look at this picture and pretend that disk has 3 dots on it. Pretend you're standing at one of those dots. Okay. What I'm going to do is I'm going to move that in one revolution. Okay? And again, pretend you're standing at one of those 3 dots. Okay, so we're going to go all the way around one time. Okay. All those dots just made one revolution. If you compare the amount of time it took for the middle dot to make one revolution to the red dot to the outer dot, how do those times compare?
They're all the same.
They're all the same. They all did one revolution in exactly the same amount of time. But which one went the farthest? The outside one. Now we have a problem. Because if you think about speed as distance equals rate times time, then that means distance divided by time equals speed. Well, we just all agreed that they all did one revolution in the same amount of time, right? But we said the outside dot was traveling farther than the red dot, which was traveling farther than the dot in the middle. So, what would that mean?
That's not true. Never mind.
Well, it's still true. The formula is still true. But what does it mean if something travels farther in the same amount of time than something else?
It's going faster.
It's going faster. So if you think about the speed of these 3 dots, the way I'm explaining right now, the dot on the outside is going faster than the red dot. And the red dot is going faster than the dot in the center. Well, that's kind of weird because they're all on the same disk, And now you're saying different parts of the disk are going different speeds. So to avoid that problem, that's why you use angular velocity. Then we can say the speed of all these dots is maybe 60 revolutions per minute. Maybe it took me 1 second to go all the way around. Okay, so they're all traveling at 60 RPMs. But they have different linear speeds. And that's where that can get confusing. Okay, so that's why you use angular velocity. In your book, if they say to find the angular velocity of something and they do not tell you the units to use, always assume radians per whatever the time is. Radians per second, per minute, per hour. Okay, time can be anything. But we assume radians unless they tell us otherwise. So comparing that to linear speed, that's the kind of speed you think about, like driving in your car. Like you don't pay attention to your tachometer to make sure you're not speeding. You don't look at your RPMs. You look at your linear speed. Okay, miles per hour, feet per second, kilometers per hour. And if you want to think of a really good connection between the two, pretend like you had a rock, okay, tied to a rope, and you started swinging the rock, okay, in a circle on the rope. Well, maybe you're swinging that rope 60 RPMs. It's going around once every second. If you were to take that rope and all of a sudden let go, the rock would take off in a straight line. Whichever, wherever you let go would go in that direction. Well, that would be the linear speed. That would be instantly converting something that's angular speed to linear speed, okay, by letting the rope go. That's basically how that would work. Okay. Another idea for that is if you had some kind of tool, like let's say you had a belt sander. But don't try this. And maybe the belt on the sander goes around, 500 RPMs, makes 500 revolutions on the sander per minute. Well, if you put that belt sander on the ground, and all of a sudden it took off going straight, that would be converting the RPMs of the sander into a straight speed. Okay? That's the connection between the two. Again, don't try that. Okay, so we're going to convert between the two. And you can come up with all kinds of fancy formulas to convert and equations, and that works fine, but it's a lot easier if you just use this technique, looking at your dimensions. Okay, and the big idea with dimensional analysis is if you have fractions and you want to cancel something out, you put it in the opposite spot. It's exactly the way I taught you how to change degrees to radians. Degrees is in the top. If you want it to cancel, you put it in the bottom. That's all you have to really keep in mind. Okay, for this, you do have to know basic conversions. You have to know how many minutes in an hour, how many seconds in a minute, okay, that kind of stuff. If it was a really weird conversion, like how many kilometers in a mile, that's not as common, I would tell you what it is. Okay, but basic ones I expect you to know. Okay. So let's start with something very, very simple. Okay, this isn't even a rate. It's just a measure of time. Okay. There's no distance with this at all. Just 3 days. Okay, not 3 days per minute or 3 days per second or nothing like that. Just 3 days. Okay, and I want to convert it to minutes. Just going to make it a fraction. Okay. If you convert 1 unit at a time, what's the next unit down from a day? Heading towards minutes. Hours. So now, what I'm going to do is try to come up with a fraction here that relates days and hours. So I'm trying to make it smaller. I want days to cancel. And I'm going to turn it into hours. So where would days go? They would go in the bottom. Hours would go in the top. Now we need the formula, the conversion between days and hours. What's the connection? 24 hours, 1 day. And now days cancels. If you did that calculation out right now, you would have hours. Okay. What's the next step down from hours? Yeah?
60 minutes.
So 60 minutes in an hour. So 60 minutes in 1. So we have to decide if the 60 goes in the top or the bottom. The way I do it is figure out where the dimension goes first. Where should hours go so it disappears? Bottom. So hours is in the bottom. Minutes is in the top. And Colleen just said 60 minutes in 1 hour. Okay. Now you just multiply straight across. So we've got 3 times 24 times 60. Okay, so it's 4,320 minutes in 3 days. Any question on converting days to minutes? Okay, let's look at the next one. Okay, this one has one more step in it because now instead of just being a single unit like days, it's feet per second. There's 2 units. And what does that mean? You travel 50 feet in how many seconds? 1, right? It's 50 feet per 1 second. So let's write that as a fraction like this. 50 feet in 1 second. So now you have to convert 2 units. You have to get feet into miles. And then you have to change seconds to hours. Okay, you just do one at a time. Let's start with feet to miles. Where would I put feet so that it cancels out? Bottom. Miles in the top. What's the connection between how many feet and a mile?
5,280.
Yeah. So 5,280 feet in 1 mile. If you stopped here, what would your units be? You would have a speed in miles per second, which is fine, but it's not what they asked for. They asked for miles per hour. So now we're going to convert seconds to minutes. So where would seconds go? Top or bottom? Top. How many seconds in a minute? 60 seconds, 1 minute. If you stopped here, you'd have a speed in miles per minute. We gotta go one more. Minutes to hours. Where would minutes go? Top. Hours in the bottom. And the connection between minutes and hours. 60 minutes, 1 hour. And minutes is gone. Now look at the units that are left. Miles per hour. Okay, so let's see what you got. We've got 50 times 3,600. That's 60 times 60. Divide by 5,280. So if you're going about 34.1, you can either write like this, or you could just
What
put
did you multiply?
MPH.
Multiply 50 times 60 times 60 divided by 5,280.
Yep.
Alright.
So if you're traveling 34.1 miles per hour, you're traveling 50 feet every second. Any questions on that one? So the last one, for this, and then we'll see what we get to in section 6.2, and we'll finish tomorrow, is going to involve an angular speed. Okay, so we kind of worked our way up. We started with just a basic unit, then we went to a rate that you're familiar with. Now we're getting into something that's a rate maybe a little less familiar. This is a speed of 200 radians per second. And now they want me to convert that to revolutions per minute. Let's start with converting radians to revolutions. Okay? And then we'll worry about seconds to minutes.
So radians would just be 180 and revolutions would be 360, right?
So if you're thinking 180, that has to do with degrees. If you wanted to change radians to degrees or something else. But what's the connection between how many radians in one revolution? Close, it's 2 pi. Okay. 2 pi is 360 degrees. So 2 pi is 1 full revolution. Okay, so that's a conversion that you have to know. 1 revolution equals 2 pi radians. Now you've got revolutions per second. And now how would we convert seconds to minutes? 60 seconds over 1 minute. Now, if you do this out, you'll have a speed in revolutions per minute. And a lot of times they write it as RPM. Okay. So let's see. 200 times 60 divided by 2 pi. So in this calculator, I can just do divide by 2 and then divide by pi. If I had a pi button, I would have used it, but that's more than accurate for what we need. Okay, so it's about 1,910 revolutions per minute. Okay, any questions on that one?
So did you just do 200 times 60 divided by 2 pi?
Yes.
Alright.
Yep. Okay, and the last one. Okay, this is going to be one like, okay, you're swinging the rock over your head on a rope. You're going to let it go, and I basically want to know how fast would it be going. So we're basically going to convert an angular speed to a linear speed. This is a little different, but same idea. You have a wheel rotating at 1850 RPM. So pretend you had a machine spinning a wheel at 1,850 RPM. All of a sudden, you knock that wheel off the machine, it hits the ground. It doesn't lose any traction, it just takes off straight. Basically, I want to know how fast it would be going. Now, it's very important that I tell you the size of the wheel. Okay, that makes a big difference. Let's just do part B. We just did part A in the last problem. Converting between radians per second and revolutions per minute. We just did that, so I'm not going to do that again. So let's find the linear speed in feet per second. If you really wanted to know how fast it's going, you'd probably want miles per hour because most people can visualize miles per hour and how fast that would be. But we'll just do feet per second. All right, so we're starting with 1,850 revolutions in a minute. Okay, let's do the easy one first. We have to change minutes to seconds. How do we change minutes to seconds? 60 seconds in the bottom, and what in the top? 1 minute. Okay, so now we have a speed in revolutions per second. But now we have to make the jump from revolutions to feet. If you have, so let's pretend this is our tire. And you mark a point on that tire. You know, it might be easier just to mark the bottom. Here's the ground. Okay, and you roll that tire along the ground until that mark gets back to the bottom again. The distance between these two marks is what we're trying to figure out. How far is it between those two marks if that tire rolls one time and then stops? It's the circumference. It's the circumference of the tire. The bigger the tire, the farther it's going to roll. Really, really small tire, think of something that's like a pen. If it makes one revolution, it doesn't roll very far. So, what we want to find is the circumference of the tire. Okay? Because that distance tells me how many feet in one revolution of the tire. It tells me the circumference of the tire. Okay. What was the radius of the tire?
18 inches.
18 inches. And let's just do, what's 2 times 18?
36.
So there's 36 times pi inches in one revolution of the tire.
Why times pi though? Why don't you just do 36?
Well, the circumference is 2 times pi times r. That's from geometry. That's the circumference.
Yeah.
So 2 times the radius gives me 36, but you still have the pi. Okay? So we don't have to figure out what that is. It's 36 times 3.14. That's how many inches in one revolution of the tire. That's how far it would roll on the ground if you rolled it one time. Okay, so let's write that down. We just figured out in one revolution, there's 36 pi inches. Now, that's a conversion that will change with every problem. There's always going to be 60 seconds in a minute. There's always going to be 24 hours in a day. That stuff doesn't change. But how many feet in a revolution depends on what's revolving. Is it a big tire or a small tire? Okay? So that's the conversion. You have to figure that one out every time using circumference equals 2 pi r. Okay, so there's that many inches in a revolution. And then the last step, how many inches in a foot?
12.
12. Make it a little bigger. All right, so I have 12 inches in 1 foot. And now inches cancels. Look at the unit. What's the only unit left in the top?
36. Or 8.
Feet. What's the only unit left in the bottom? Seconds. That's exactly what they want, feet per second. So I'm not going to do it, but you just go through and multiply 1850 times 36 times pi divided by 60 and then divided by 12. And whatever you get, that would be the speed.
So you should do the 1850 divided by 36 pi over 60, then divide all that by 12.
1850 times 36 pi.
Yeah, 30 times 36 pi.
And then divide that by 60 times 12. Yep. Which is 720. So you divide by 720. Okay. Any questions on that? It takes a little practice to get used to the conversions, but it's not too bad. All right, so last thing we'll look at, we're not going to finish today, so we'll start it, and then whatever we don't get to, we'll just finish tomorrow. Okay, so section 6.2, okay, the name of that section is unit circle trigonometry. So the whole idea of unit circle trigonometry is you can take, move this away for a second. You can could take any circle, okay, and draw an angle inside it, okay, like this. And when you draw that angle in it, the terminal side is going to hit the edge of the circle somewhere. In that particular angle, it hits it right there. Well, that point has a coordinate. And that's the goal of unit circle trig. Figure out that coordinate. And that's it, basically. That's the goal. You draw an angle inside the circle and find the coordinate for where the terminal side hits the circle. Now, some coordinates are easy to find, some are a little harder. Let's start with some easy ones. And we did this one actually in the homework. Where's 90 degrees? Yeah, we did the one 0, 5. If it's on a unit circle, the radius is only 1 unit. So the coordinate is up 1. Okay, unit circle is 1 unit in every direction. So that's 90. What angle would that be?
0, 0.
Well, the angle would be 0, 0 is right in the middle.
1, 1. Wait, no.
That's the angle 0 degrees. That's when the initial side is right here. The terminal side is right there. You don't even really have an angle. So what would the coordinate be?
1, 0.
Yeah. That's always the coordinate for 0 degrees. How about if your terminal side was over there? What angle would that be?
-1.
That's the coordinate, which is the important thing, but what's the angle?
Oh.
180. And what about if your terminal side was down here? What angle would that be? Angle, not coordinate. 270. But the important thing is the coordinate. -1, 0, -1. Those coordinates never change. Those are always the coordinates for those 4 points. And they're the easiest points to find because they all have a 0 in them. And the other number is either a positive or a -1. So any questions on those 4 coordinates? Now, it's not wrong when somebody said, well, couldn't this be the point 0, 5? Yes, it could be if you had a circle that was bigger. Okay, if you were dealing with a much, much bigger circle, 0, 5 would be 90 degrees. But we're dealing with a small, very small circle where it's 1 unit in every direction. Hence, unit circle. So I already said this to you. Basically, the goal is to find the coordinate, and we just practiced that. All right. So, what does the coordinate allow you to do? Well, the coordinate is going to have 2 numbers in it. What do you call the first number? You call it the x. And what do you call the second number? You call it the y. So in the case of 90 degrees, the x is 0, the y is 1. In the case of 180, x is -1, y is 0. Well, what the coordinate allows you to do is that. Okay, don't worry about that. The x and the y value of the coordinate allows you to find the 6 trig functions of the angle that you drew in the circle. What's the angle? Well, that thing in red, okay, whatever the angle is. That would be a harder coordinate to find because it's not lined up nicely on an axis. Okay, so we're not going to do that yet. But that's what the coordinate allows you to do. It allows you to find one of the 6, or all of them if you want, the 6 trig functions of the angle that you drew. All right, so if you drew an angle like that, and I said to you, okay, in the angle you just drew, I want you to tell me the sine of that angle. Well, the first step is you look at what you drew, and you have to figure out that coordinate. If you can't figure that out, you can't do the unit circle trick. Okay? You have to be able to figure that out. Okay. So once you have your coordinate, you plug it into the formula. And for some people, this might be the first time they've seen the trig functions. I'm guessing a lot of people probably have seen or heard of these before. But if I happen to ask you for what's called the sine of the angle, after you find your coordinate, all you would have to tell me is the y value. For sine, you don't need the x. If I asked you for the cosine of the angle that you drew, you take your coordinate and you write the x value down. That's called the cosine. Now, if I ask you for the tangent, you need both. You take the y value of your coordinate and you divide by the x value. And I wrote the abbreviations that you would normally see. Sine is SIN, cosine is COS, tangent is TAN. And that's how you'll see the buttons on a calculator. See when we use a calculator. The other three trig functions are very similar to the first three because all you have to do is, if you pretend that was a fraction, you flip them. So the cosecant, abbreviated CSC, is 1 over y. So take your y value, flip it. Now, if this pattern continues for the other two, anyone think they could tell me what the secant would be? Yep, it'd be 1 over x. And lastly, the cotangent is the reciprocal of the tangent, which means flip. So the cotangent would be x over y. So no matter which one of these 6 you want to do, you have to find the coordinates. So we'll practice one or two finding the coordinates and then figuring these out. Everybody have the 6 definitions of the trig functions? Okay, those first 4 angles, I didn't mention it earlier, but those are called quadrantal angles because all of them are on the axes. Okay, so 0, 90, 180, and 270, there's a special name for those groups, that group of angles. It's called quadrantal angles. It's not super important that you know that word, but I might use it at some point.
Would 360 fall into that?
360 would be a repeat of 0 because it's coterminal.
Oh, yeah.
Yep. Okay, so how do you actually do unit circle trig? Step 1, to do unit circle trig, find the coordinate. In some problems, they'll give you the coordinate. If they give you the coordinate, you're good. You don't have to find it. Okay, so step 1, find the coordinate, or if they give it to you, recognize that they gave it to you. Step 2, take the coordinate and plug it into one of these formulas, whichever one they want you to find. Okay, I'll do one where I practice all 6 so you can see how to do each one. Okay, so again, step 1, find the coordinate. Step 2, plug it in. That's it. Okay, let's look at this one. In example 1a, did they give me the coordinate? Yeah, they gave it to me. That's x, that's y. Which trig function is it asking me for? It's asking me for all 6. Now on a test problem, I wouldn't do all 6 in the same problem. What's our definition of sine? What does sine equal? Ezekiel?
0.
Can you just give me the definition first, and then I'll ask for this particular problem. Sine equals y. So what's y in this problem? 1. What's the definition of cosine? X. What's x in this problem? 0. What's the definition of tangent?
Y over x.
It's y over x, which is 1 divided by 0. What do you get when you divide by 0?
Undefined.
Undefined. Now, once you get the first 3, what did I say you do with each one of them to get the next 3? Just take and flip them. Now, I know 1 isn't a fraction, but if you wrote it as a fraction, it would look like that. What do you get if you flip 1? 1. 0 as a fraction would look like that. What do you get if you flip 0 over 1?
0. Oh, undefined.
1 over 0, undefined. And now, the cotangent? Well, the tangent was 1 over 0, so when you flip it, you have 0 over 1.
Which is 0.
That's okay. Yeah, that's 0. So there are your 6 trig functions of the point 0, 1. This will be the last one. What's different about this example compared to the last one? They're giving you the angle, which is great, but that's not what you need. You need the coordinate. Does anybody remember on the picture, what was the coordinate for 90?
0.
0, 1. So the first step is to find the coordinate, and now we just did that. We just did 0, 1 in the last problem. So now you would go through and write all the same answers again. The only extra step is you had to know that yourself this time. I didn't tell it to you. Okay? So we can practice some more of these tomorrow if we need to. When we go over homework, we'll do some more. Okay, so the homework on 324, that's the first end of the first part we did. 56 to 59, 70 and 71. And then on page 335, there's only 3 problems in the book, 1, 5, and 8. But I want you to do what they asked you to do in the book for 1, 5, and 8. But I also want you to do what we just did. Find the 6 trig functions of 1, 5, and 8. Find the sine, the cosine, the tangent. Okay? And try to find the 6 trig functions for 3 pi over 2, 2 pi, and that coordinate right there. So you're going to have to figure out the coordinate for 3 pi over 2. And I'll give you a hint. It's a nice one with a 0 in it. And you're going to have to figure out the coordinate for 2 pi. It's another nice one with a 0. The last one, I just gave you the coordinate. Okay, so we'll take a look at that tomorrow.